What we now know is basically every star has a planetary system, and some significant fraction of those planets could bear some resemblance to the Earth or be similar enough to create equivalent conditions that might allow life to happen. Wouldn't it be remarkable just to know that life happens elsewhere in the universe, even if it's the simplest, humblest microbe? I personally, that to me is a very deep and important question.
Caleb Scharf, how did your work as an astrobiologist lead you to write your previous book, The Ascent of Information?
The previous book I wrote, The Ascent of Information, is about the idea that humans are interesting as a species that generates and carries through time this extraordinary body of information. It's not in our genes, but we inherit it, and it persists with us through time. And I called this thing the Dataome, sum total of our externalized information. And the reason I ended up writing that book actually was because of my professional work in astrobiology. Astrobiology is about the quest to discover whether or not there is other life in the universe, and to also understand the nature of life and living systems. And the idea for the Ascent of Information came out of my thinking about what it is that makes intelligent life possibly special or different than other types of life. And this was motivated by ideas of looking not just for things like microbial life in the universe, but looking for signs of technological intelligent species out there. And it seemed to me that one of the unique characteristics of us, which might be a universal characteristic, is this capacity and trait of building an externalized informational world that we carry through time with us. And so that might be something we look for elsewhere in the universe. And then that got me just thinking, well, what do I mean by externalized informational world? And that's where the book came from.
And what did you conclude? Is externalized information the key to intelligent life?
I think it could be. So the book took me in some interesting directions, and really the most, I suppose, the boldest and biggest conclusion that I had was that our externalized information, this thing I call the dataome, which is the sum total of every written word, every architectural item that we produce, all of our sort of externalized information that we carry through time, has the hallmarks of being a living thing itself, and that we really exist in a type of symbiosis with that externalized information. And like any symbiosis, sometimes our interests are aligned, sometimes our interests are not aligned. And I think a great example today would be seeing the extraordinary energy demands of our informational world, in particular things like AI and big data demand these huge data centers consuming energy like nobody's business. That's clearly not really ideal for us, although we gain many benefits from AI, from data, and so on. So I would look at that as an example of where we're in this symbiotic relationship, and right now the information is winning. It's getting what it wants, possibly to the detriment of us.
Yeah. What other conflicts would there be besides storage and energy around the information?
Well, I think, information, if you see it as a potentially analogous to a living system or even a truly alternate form of life, I mean, that's not an unreasonable hypothesis, then much like biological life, its interests are really more about the things that create opportunity for it to persist, opportunity for it to reproduce, and so on. Some of the other things that might happen is, information doesn't necessarily care about whether it's useful to us. It just cares that we continue to propagate it. So disinformation is just as good as real information from the point of view of a sort of informational organism. And in fact, as we know, disinformation is propagated just as easily, if not sometimes better, than information that has some bearing on physical reality.
Yeah, bad news spreads faster, and disinformation often comes in the form of bad news.
Absolutely, absolutely.
So there's this idea that information manipulates us. And you have an interesting anecdote about going to the place of Shakespeare and maybe being pulled by information there. How does that work?
Yeah, so again, this is seeing information as a part of a symbiosis with us, as another system, another type of living system. And the anecdote I had was, and it's part of how I start that previous book, The Ascent of Information, is talking about my experience going to visit the birthplace of Shakespeare, going to Stratford upon Avon in the UK, and sort of dragging my family along and spending the day doing all these things, traipsing between different buildings, looking at the tourist knickknacks, going and buying a pastry at one of these bakery shops with some pretension of being related to Shakespeare somehow, or utilizing some of his wonderful turns of phrase. And then by the end of the day, standing there looking at the epitaph on Shakespeare's grave, his tomb in the church in Stratford upon Avon, and suddenly realizing, well, you know, Shakespeare didn't do this to me. He didn't force me to spend my day and my energy doing all of this. It's actually all the products of his ideas, his writings, his informational world has outlived him. And that's so obvious in retrospect. It's completely outlived him. And it's forced me, in a way, to do all of these things today. It's forced me to walk through the streets. It's forced me to buy the pastry. It's made me sort of visit these different museums and so on and be immersed in this sort of world of Shakespeare. And that's really interesting and, slightly disturbing that he's reached across the centuries through his intellectual output, through his information to control me. And at many points during that day, I didn't feel entirely in control. I felt obligated to follow that thread. So, yeah, so that's part of this idea of being manipulated, being coerced by information that is well adapted to our human tendencies to follow patterns, to find intrigue in things. And it's for the betterment of that information, because I've helped continue the propagation of that information by my action.
Mhm. And on a micro specific kind of level too, even that epitaph is in a way sort of manipulating the reader and making sure that that place is untouched. For those who aren't familiar, I copied it down. It's, "Good friend, for Jesus' sake forbear to dig the dust enclosed here. Blessed be the man that spares these stones, and cursed be he that moves by bones." It's this sort of lasting echo of, hey, don't mess with me, and I'm putting it through information that will last longer than these bones.
Yeah, no, it's this extraordinary and sort of threatening, ominous statement that, yeah, yes, exactly. Don't mess with me. And it worked well. It's a weaponized type of information because it suggests that there'll be consequences if you don't obey, which of course is ridiculous, but it works.
Yes. Yeah. So this sounds a lot like Richard Dawkins' sort of selfish gene idea, and you have distinguished between the dataome and genetic information. So what are those differences there? How do they compare?
Well, so I think the most striking difference between genetic information and what I call the dataome is, of course, that genetic information has a built-in mechanism to be propagated through time. It is part of our code, and so there is a molecular basis for its continuity through time, and it's internalized, right? It's part of our interior composition. The difference with the dataome, this externalized information, I think, is that it relies on aspects of the organism that produces it, such as language, such as symbolic representation in the external world, which is not quite the same as how genetic information propagates and has propagated for the last 4 billion years on the Earth. So the dataome is interesting in that it is, in a sense, less constrained because it can also be instantiated in many different ways. Genetic information is genetic information. It's embedded in DNA and RNA and in our molecules. The dataome, it can be on a clay tablet, it can be in a printed word, it can be in electronic bits in some silicon substrate. And so it feels like it's a further evolution, if you will, of how information can propagate itself in the universe. Information, at least here on Earth, has propagated itself in molecular structures in biology. And now it's almost like it's escaped. It's found a way to propagate itself in many different forms, which is potentially a turning point in the history of life on the Earth. And so in that book, in The Ascent of Information, that's something I explore. That is this one of those big evolutionary transitions, such as the oxygenation of the Earth's atmosphere and the different biochemistry that enabled, is the sort of escape of information in a much more dramatic way than it has happened before, escape of information from biological entities into other forms. Is that a transition point for life on Earth?
Yes, and many thinkers talk about the idea of an information explosion and we're going to sort of transcend information. What do you think about that in terms of where we stand in history?
Well, I think we may be at a point where there is a leap or a transition to a world where information has truly managed to jump to a different substrate. And that different substrate, as I think we might imagine looking around at our computational world at the moment and its energy demands, is changing the balance of fundamental qualities of the planetary environment and the planetary sphere, if you will. So we have the biosphere, but we also have this technosphere. Sometimes it's called the noosphere, meaning a sphere of the world constructed by technology, by artifacts of other life, of organisms like us. And up until fairly recently, the biosphere was the dominant sphere on the planet. We now know that the technosphere, for example, the mass of matter embodied in the technosphere now equals or exceeds the total mass of matter composing the biosphere on the planet Earth. That seems to me like a point of transition, a point of drastic change. And it may not be a coincidence that we can look at our own technology and feel that it's just changing at an exponential rate. And of course, the growth in modern AI is a good example of that. I mean, 3 years ago, we weren't really talking about this, and now it's a part of, for all of us in the world who have access to computers and the internet, it's an integral part of our life. So I think, ideas of a singularity, of a dramatic shift in the nature of life on Earth have been around for a long time. I think the difficulty is always, how do you predict that change? I mean, and I think it's happening in a way that we perhaps couldn't have predicted. And it's happening to some extent stealthily, but does seem to be happening right now.
And humans going into space, going to the moon, things like that, how influential do you think that is in this grander picture of humanity?
Yeah, so I think, the transition of life from its point of origin into the universe around it is also a major event in the history of life here, and it could be the same for the history of life elsewhere in the universe. And that's part of the idea behind this new book, The Giant Leap, which is asking, what are the real implications when a species learns how to climb away from its planetary surface and start doing things in space? And I think, people have recognized for a long time that this is an important thing, right? Back in the midst of the space race in the 1960s, 1970s, people enthused about a future where we're living on Mars or living in space stations and so on. But it was a slightly different context. The way I've been trying to understand this is almost through a natural history of space exploration, to see it as a phenomenon that has emerged out of a species, us, and is one that potentially causes another transition in the nature of life. And I think there are many facets to that. There are the aspects to do with how being in space creates a vastly different set of data and information about the Earth that has transformed us. It is continuing to transform us. This is from satellite data, it's from communications, it's from navigation, all of those things enabled by putting satellites into space around the Earth. But there's more to it than that. I think that as we explore further in our solar system, we learn more about the nature of life. We learn more about our technology. We develop more technology that we wouldn't have developed otherwise. And all of that comes back to affect the nature of our existence here on the Earth.
And you've met Buzz Aldrin. What was that like?
I did have the privilege of meeting him. This is quite a few years ago, and I talk a little bit about it in the book. It was, for me, it was extraordinary. It was sort of a dreamlike experience. I mean, he's a very personable guy. He's a very interesting person. He's very bright. But I had to constantly pinch myself that I was sitting with this human like me, except this human has set foot on another world. And so I was a little bit starstruck, I have to confess, and I try to describe that a little bit in the book. But it was also a very moving experience for me, because my impression was that for him, that entire experience, obviously he had been in space around the Earth, but then going to the moon and being the second human being ever to set foot on another world, was profoundly important and changed him. And I came away, and this may have been my own imagination, with the sense that if he could have the opportunity to go back again, he would in a flash. There was something about that experience that was so profound and strange and important. Again, that could be me projecting, but yeah, it was a very interesting experience. Some of it, the conversation with him was in some ways very ordinary and sort of chit chatting about science and so on. But yeah, for me, sitting there and just, I kept wanting to shake his hand and to make contact with this being that had been somewhere truly alien. Very very special experience.
And you compare this to natural history, and in your writing, you use the model of the Voyage of the Beagle. What are the connections there?
Yeah, so I think the Voyage of the Beagle in the book came about because I was trying to understand the context of space exploration, the history of space exploration so far, and what it has changed in us and what may happen in the future. And then gradually I came to realize, well, seeing it as a natural history makes sense. Are there parallels in the past exploration of the Earth and in our sort of intellectual exploration of the world that would be useful to look at? And the Voyage of the Beagle, so this was the journey that Darwin took part in the early 1830s, where they literally spent 5 years sailing around the world on this very sophisticated vessel. So that was interesting, that it had parallels to modern space exploration, just the construction of the Beagle itself. It was a modified ship. It was sort of decked out with the latest and greatest scientific instrumentation. Even it had, copper plating to prevent lightning from damaging things. It had, they replaced the cannons that had been made out of iron with brass, because that would affect the magnetic fields of the Earth less, so their compasses would be better. It carried 22 clocks, 22 chronometers to help with navigation, because you use clocks to peg your longitude. And so it was interesting in almost a sort of trivial way, as this is the nature of exploration with spacecraft, where you have these intricate technological machines designed to support humans, designed to gather information, designed to navigate, clearly paralleled what was already happening in the 1800s with a research vessel like that. But then at a deeper level, I realized Darwin's experience on the Beagle is a good parallel to our experience in leaving the Earth and exploring the rest of our solar system, in that he was exposed to environments he had never imagined. He was exposed to living systems he'd never seen before, species he'd not encountered before. He was exposed to this, if you will, the sort of overview effect of the planet. And in space travel, people talk about the overview effect. Astronauts talk about this, that experience of, if you're in the space station, for example, orbiting around the Earth, you see the Earth as a whole. You don't see the divisions between countries. You just see continents and oceans, and you grow an appreciation of the extraordinary interconnectivity and unity of the Earth, of life on Earth, and so on. And I think Darwin got some of that from the Voyage of the Beagle. So that, in terms of telling the story of space exploration, was a useful parallel. The slightly deeper sort of intellectual academic piece of it is that a consequence of the Voyage of the Beagle was eventually Darwin formulated his ideas about the origins of species and a theory of evolution. The Voyage of the Beagle gave a lot of important input to that. And I would argue that Darwin's vision of evolution, his theory of evolution, also caused change in our species. His theory of evolution caused evolution. Those ideas about how you breed plants or animals, how things are inherited generation to generation, how species evolve, how they adapt, how selective forces change things, how feedback from the environment modifies biology. Having those ideas caused us to change our behavior as a species. We changed how we dealt with our food stuff and animals. We changed our ideas about even economics, how feedback and evolution takes place in economics. It changed our understanding of biology. We went in search of the molecular basis of inheritance in DNA and so on. And we also developed ideas that played a role in modern artificial intelligence, the idea of evolving feedback-driven self-programming algorithms comes really straight out of Darwin's ideas about evolution. I would argue that space exploration is doing the same sort of thing. It's modifying our behavior. It's changing our ideas about how we do things on the world. We all pick up our phone to navigate from A to B, or to call the Uber to pick us up, and so on. And that's a consequence of having space-based facilities to enable things like navigation and communication. And so it is evolving us. So there are all these beautiful parallels between the Voyage of the Beagle and these ideas about what's happening with space exploration that I wanted to explore.
Yeah. So we see this connection between this sort of naturalist endeavor and the Voyage of the Beagle and what you're talking about now. I wonder, is there also a feedback loop like this? We shape tools, tools shape us. Does your work shape science fiction? Does science fiction shape your work back?
I think the obvious answer is yes, in both directions. Science fiction has, of course, explored the ideas of space exploration since long before we actually had the capacity to do it. And the beautiful thing about science fiction is that it can let you ignore some of the details, but think about what the consequences would be. And that does motivate people. It motivates scientists, it motivates technologists, and so on. And of course, as scientific discoveries take place, that in turn leads to new science fiction. I mean, I think, the discovery of DNA, deeper understanding of the molecular basis of life, suddenly you had science fiction that was talking about the manipulation of DNA, the manipulation of organisms into new forms in a way that hadn't really existed before, and so on and so forth. So I think, to me, science fiction and science are really closely linked, and there's a beautiful synergy there where the interface between science fiction and real scientific research is that frontier edge. It's that place where you can test ideas, where you generate new hypotheses, some of which may not really make any sense, but it's okay because a good hypothesis is a hypothesis that can also be disproven easily. And so it's a really fertile ground, I think. And space exploration, science fiction absolutely have clearly had a strong connectivity for a very long time, going back to H.G. Wells and going back even earlier, Jules Verne and so on. The idea of what would it mean to be able to leave the Earth, to go to the moon. And of course, in some of those early science fictions, the assumption was there might be other life on a place like the moon, and it would be different. But how would it be different? And so all of that fictional work has been an interesting sort of proving ground for thinking out of the box about the nature of life, thinking out of the box about the consequences of space exploration, for sure.
We get specific, what sci-fi do you like? What sci-fi do you think was maybe ahead of its time or had a great vision that turned out to be right?
Gosh, I like all sorts of science fiction. I tend to veer towards what would be called hard sci-fi. So that is science fiction along the lines of, classic like Arthur C. Clarke, for example. Clarke was remarkable in that he, had a strong technical background and also a capacity, a sort of very humanistic way of thinking about things. I mean, he was interested in the way societies operate and what that would look like in the face of very different sort of environments and technological abilities. So, some of his stories, I mean, he essentially presaged the rise of geostationary satellites, the idea of communication using satellites in space sort of came out of his thoughts. Some of it was technical work on his part, but it was also fiction. And he wrote stories about, asteroid miners way back in the day. So he foresaw the possibility of things like asteroids as being resources, both for the Earth and for a sort of a space infrastructure. So he explored, well, what would that look like? What would people who are asteroid miners be like? What would their society look like and so on? And he also talked about more extraordinary things like space elevators. That was one of the areas that he, in a sense, helped develop, because in order to write his fiction, he wanted it to have some basis in fact, some relationship to reality. So he thought about the engineering issues of building a space elevator and so on. So I definitely like writers like Clarke, more contemporary writers. I love Alastair Reynolds, who is also a former, well, a scientist. He trained as a scientist and now writes really wonderful, hard sci-fi that really pushes the extrapolation to the extreme, thinking about galactic civilizations, thinking about a point where many of the constraints on where we place our minds and where we send ourselves are sort of removed because of technology. I love that kind of stuff because I think it melds deep questions about the nature of life with these sort of speculative ideas about what the future might hold for us.
Yeah, and the future of life, I mean, that's so much of your astrobiology. You mentioned the overview effect. I wonder, let's say we colonize Mars. If we have that sort of overview effect, if we start to see people on Mars as living on a different planet, will we see them as no longer humans? Would we see them as Martians or something else?
It's a very interesting question. I mean, look, so, right, we humans do have a bad tendency to look at others who are clearly humans, but maybe they live somewhere else, or they speak differently than us, or there are some superficial physical features that are different, and immediately they're an other. So we definitely have that tendency. Um, yeah, I think the idea of having humans inhabit another world or something elsewhere in the solar system is really, really interesting. What would our perception of them be? I think to start with, it wouldn't seem so strange. We'd see of, them as just, well, yeah, it's the people on Mars, right? But what happens a few generations down the line? One of the things that could happen, actually, I think, and I talk a little bit about this in the book, it doesn't just apply to Mars, it applies to human spread out into the solar system, that there will be actual biological evolution that takes place. Sort of dispersing us out into fresh terrain will inevitably cause changes in the environment for us, wherever we are, and those changes will inevitably cause selective changes. They will cause biological evolution. So there may come a point in the much further future where actually it's valid to say, well, yes, that species on Mars, they used to be like us, but they're not so much anymore. Yeah, so I think there is a lot of interesting, potentially bad, potentially good things that would happen if you started to have different pockets of humanity spread on these larger scales. I mean, we've had pockets of humanity on the Earth for a long time, but we are all still on one planet and much more connected than when you start spreading us onto other planets or elsewhere in the solar system.
To make that expansion, how important is artificial intelligence for getting humans distant off Earth?
Well, I'll confess this is something of real interest to me in my own research, so I'm somewhat biased. I think we're just beginning to really consider the potential and the opportunities from artificial intelligence or machine learning more generally. I mean, I think, we in popular usage, we conflate things like, large language models like GPT and so on with AI and also with machine learning. But machine learning, which includes, as part of AI is, can come in many, many different forms, including approaches that, are not yet on your Insta feed or anything like that, but they're to do with data analysis and data or prediction from data and so on. I think the nature of space exploration absolutely lends itself to sophisticated AI, whether it is AI that is crunching data, whether it is AI that is actually sort of incorporating, much like GPT or these other large language models, a sort of corpus of human information to try to make decisions based on circumstances. I think it could be incredibly important. Already we're thinking, in science, we're thinking about autonomy in space exploration. And autonomy is key because of the distances involved. If we have a probe out at Saturn, for example, signals may take 20 minutes to get back to us and vice versa. And so real-time control of things is very difficult. What's really intriguing and extraordinary is the possibility of AI systems that are not just sent to, keep the spacecraft safe, take some pictures, follow this procedure, but are sent with a purpose, and a purpose being, we want to resolve these scientific questions. Can you please figure out how to do that? And I think we're starting to see the beginnings of a scheme or schemes for doing that, where the AI will be tasked with essentially a research question. We'd like to understand the interior structure of Enceladus, one of the moons around Saturn. Now, please go and do it. Here's a spacecraft with a bunch of instruments on it. Go and figure out how to do this. It's not ridiculous to imagine that that's how we might do things in the future. And so the AI would have control of the spacecraft, have decision making about what measurements are taken, when they're taken, how the spacecraft is moved or adapted to best serve the overarching question that we give it. And that to me is pretty extraordinary and exciting, because it's a way to create artificial scientists that can do things we can't. They can live in a vacuum. They can live in a radiation environment. They can live essentially disconnected from us back on Earth, except occasionally sending back reports on what they've done. In fact, I think they would just send back fully publishable papers, because why not?
Yeah. It seems in your writing, too, that some of the brilliance of the early astronaut programs was that we could put human beings in places with that sort of directive, and they had maybe basic training in fields outside of their own, but could kind of figure it out. So what is this? Is it the idea to kind of simulate that level of an astronaut?
I think in part, absolutely. Humans are really versatile. And we saw that with the astronauts during the Apollo era, and the Gemini era, and even today on the space station. An astronaut will be trained to run certain experiments. They may not be an expert in that, but a smart human can learn to do things and learn to be observant, or respond to their observations. And that was one of the things we saw really dramatically in the Apollo lunar landings, was that astronauts with a modicum of training in geology could walk around, and just their natural human tendency to observe interesting things, to notice interesting things, to notice anomalies, would lead them, combined with their sort of basic geology training, to spot rocks that look different. And those rocks turn out to provide really interesting clues to the history of the moon and so on. So I think there's still a role for humans in space exploration. I mean, AI, I think, is perhaps better thought of as a companion, right? Already, we can create agentic AI that go off and work on a homework problem for us, or whatever. Imagine on Mars, we have a mixture of astronauts and AI-controlled robots. And the astronauts can interrogate the robots. They can give them text prompts. They can say, hey, I saw this interesting thing over on that ridge. Can you go and check it out and resolve this question for me? So the AI-controlled robot will trundle off, and it may be quite autonomous, but it is capable of making inferences. it's capable of making some of those decisions, but it frees up the human to go off and do the things that humans do best, which is spot anomalies, to ask the right question, to be puzzled over things. And so I think that there's a space there for some really interesting and extraordinary synergy between humans and AI. Perhaps it's difficult to even imagine on the Earth. The Earth is a sufficiently complicated place, and it's so familiar to us that might not work as well as this sort of full-on exploration with humans and machine-driven tools.
So it sounds like the ideal AI is not 2001: A Space Odyssey. It's more Interstellar, when they had that robot that could go and pick things up and move people around and take care of stuff.
I think so. I think yeah. I mean, obviously the HAL computer in 2001 was a fabulous um, sort of piece of invention and posed all sorts of philosophical questions. But yeah, whoever had built that kind of got it wrong.
Right.
Or at least, they made the mistake of asking it to deceive, and that messed it up. Yeah, the robot in Stellar felt more akin to our modern way of thinking about how machines can work with us and yet have autonomy. And I think, that's going to be part of the future.
So another example in science fiction is Dune. And in Dune, they reference that at some point in history, there's this Butlerian jihad, and they say no more AI, but humans evolve to these very, very extreme tasks. What do you think is the potential of humans for extreme tasks in space?
Well, I think perhaps more than we imagine at the moment. And the reason I say that is that we now do know how to manipulate our genome, right? We have gene editing, which didn't exist not that long ago. We have increasingly sophisticated pharmacological solutions to problems that we run into in different environments. And while some of those have been applied to, certainly the pharmacological solutions have been applied to what astronauts experience on the space station. Microgravity is not great for a body that has evolved out of living on a planetary surface. Radiation impact on terrestrial biology has to be dealt with. Confinement, limited microbiome, microbial environment around you can influence your digestive system, your immune system, and so on. So I think we're seeing the beginnings of sort of biological manipulation that makes us better suited to being in space. And if you're in zero G, we can now, the same pills that you take for osteoporosis can help prevent your bone loss in space. And I think down the line, it may be that we can adapt ourselves quite a long way to either living in a space station or living on the surface of a planet like Mars. The interesting thing about a place like Mars is that the gravitational acceleration on the surface of Mars is about a third of what it is on the surface of the Earth. And we don't actually know what that does to you. We have some idea of what zero G does to you because of time spent on space stations. But a third G for an extended period, it's not clear what that does to us. And if we really want to stay there for a long time, we're probably going to have to, deal with that. I'm not suggesting we gene edit our way to a solution, but that could be down the line in the future. It would make sense to address that through, fundamental manipulation of our genome and the expression of those genes. You may need to switch off the expression of certain genes because it has a detrimental effect in an alien environment, or switch on the expression of others. And again, pharmacological solutions could be developed to, keep your body chemistry from going completely haywire. And I think we're just beginning to see what we could do with that.
Yes, it's interesting in reading your writing too about things like the pharmacological solution. I was an officer in the Navy, and so I also think of Navy history and things like that. And it was, these austere environments of ships that helped us to recognize things like scurvy and the need for vitamin C. And so I do wonder, how far pharmacological solutions can take us.
I think, yeah, maybe not all the way.
Yeah. Yeah, but some
And it
maybe.
may be that there has to be a sort of hybrid approach where, and I think this is something we're sort of starting to really understand is just how much we do have to engineer the environments that we live in. So, for example, you can spin up a space station and create artificial gravity using centrifugal forces. And, we haven't really done much of that yet, but that may be an important solution to issues of human physiology in low gravitational acceleration. And there may not be a pharmacological solution to that, but you could perhaps, go halfway, meet it halfway. You don't need a full Earth gravity, you need some, and then you pop a few osteoporosis pills now and then, and maybe that is sufficient.
What I'm getting in this discussion is that your field is so wide-ranging. Just to kind of ground us, what even got you into being an astrobiologist?
Yeah, so astrobiology, actually, a lot of it is not so much about space exploration with humans. It's more about the search for other life, either on other worlds like Mars or further afield. I've taken a strange pathway in science. I actually trained as a cosmologist. So understanding the universe on the very largest scales and things like the Big Bang and dark matter and dark energy and so on. And then gradually shifted my interests. And what really pushed me on to the path of astrobiology was during the late 1980s, the discovery of exoplanets, the discovery of planets around other stars. And that to me was a game changer. That was an extraordinary thing. And it meshed with these questions of, is there life out there? Because previously we hadn't even known that planets occurred very frequently. It may sound very strange in retrospect, but that was the state of things. We didn't know if there were lots of planetary systems out there or very few. And if there were very few, then it would suggest there might be very few instances where you would have life remotely similar to life on Earth. What we now know is basically every star has a planetary system, and some significant fraction of those planets could bear some resemblance to the Earth or be similar enough to create equivalent conditions that might allow life to happen. So for me, it was kind of a convergence of interests of astrophysics and cosmology and physics and astronomy with I think a lifelong interest in, are we alone? Is there anything else out there? Is there anyone to talk to? And even if they're not to talk to, wouldn't it be remarkable just to know that, life happens elsewhere in the universe, even if it's the simplest, humblest microbe? Uh, I feel, I personally, that to me is a very deep and important question. And so it kind of led me to astrobiology. And you're absolutely right. Astrobiology is very far ranging. We have to understand things like planets and star systems. We have to understand things like chemistry. We have to understand geophysics. We have to understand climate systems. We have to understand microbiology at some level. I mean, obviously, within the field, different people specialize differently. To me, that's very appealing. I love that. I love always feeling like I'm learning something new. And astrobiology is absolutely that kind of pursuit, because you have to have an open mind, but you also have to have it backed up by rigor, by scientific rigor. And that means constantly learning new things, whether it's about biology or about planets or about space exploration.
How do you even decide where to put your time?
Depends how much coffee I've had in the morning. So yeah, I think like any scientific field, any individual pursuing science, you find topics that you'll study either for a while or sometimes for a lifetime. Some people become very fixated on a single topic for a lifetime. I tend to jump between things. I try to take the temperature of the research world. So I try to keep on top of developments in astrobiology, developments in exoplanetary science, developments in space exploration, to see where there are interesting questions that could be asked. So I'm often guided by seeing where some new development or some new insight could allow me to ask a question that I've long wanted to ask. And so, for instance, this issue of AI as sort of companions in scientific exploration has kind of kicked around in my mind quite a long time. And now, suddenly, we have more and more sophisticated machine learning approaches that might let us do some of this. So I plunge into that, and you see where it takes you.
Yeah, it's interesting too that for you, this moment that sort of was a trigger was the discovery of exoplanets. So how has the science of exoplanets played into your career in sort of a feedback loop?
So I was sufficiently interested in exoplanets that I decided to start trying to do some research in exoplanetary science. And that research has touched on various areas of exoplanetary science, some to do with methods for detecting and characterizing exoplanets, which is extremely difficult, I should say. Part of the reason it took us so long to determine that there were planets around other stars is it's an extremely challenging technical task to detect planets around other stars. Planets are small, stars are big, and they're a long, long way away. So it's very, very, very challenging. So I started out by thinking about ways of detecting planets, but also trying to make predictions about planetary systems. So for instance, looking at how gravity might sculpt the contents of a planetary system over time, starting from the formation of a star and its planetary system, thinking about things like gravitational instabilities where, planets form, but they actually pull on each other so much that the system sort of self-disrupts. But that has implications for what we might observe in terms of the configuration of planets, or even planets floating between stars, planets that have flung out from their parent star system to sort of float in interstellar space. But that then also got me thinking about the characterization of planets. And so I guess each piece of research that I've done has, as you say, sort of evolved my interests and evolved what I see as priorities. And so for a while I worked with, and still do, with a larger group of people interested in creating climate models, not of the Earth, but of alternate Earths. And part of the motivation for that is asking whether there are features in planets that have very different climate conditions than the Earth, but they're still habitable planets. They're still planets that could give rise to life, but whether they have conditions that are more readily measured across interstellar space using our telescopes. The Earth is in some ways, a little dull. It's got a nice balance of things in its atmosphere, and it would be great if we could measure that. But maybe there are worlds that are in the throes of more extreme changes that would be easier to actually measure because they're more extreme. So, yeah, so I think this is true in lots of science, and it's certainly been true for me. Every step has indeed evolved my thinking and evolved the things that I've prioritized in my research. And it carries on to this day.
And for us as Earth-dwelling beings, it's very intuitive that a planet would give rise to life. But how important are planets in the finding of life?
That is one of the 64 million trillion dollar questions. Yeah, I agree that intuition tends to lead us to thinking, well, of course, yeah, a planet, if it's got the right mix of things, that's what happened on Earth 4 billion years ago, right? So planets are probably the places where life gets going. We don't know that for sure. And this is one of the interesting challenges in astrobiology is the sample size of one. We have the example of the Earth, and we do have pretty good understanding of, certainly the Earth today, and to some extent the Earth through time. It's still very incomplete, and we still don't have a fully testable, provable hypothesis for the origins of life. We have a bunch of ideas about the conditions necessary to kick life into being, and many people are working on that. And it certainly does seem that conditions on a world like the Earth, as they may have been, 3.5 billion, 4 billion years ago, those conditions, you've got water, you've got all sorts of chemistry going on, kind of seems like, yep, that's probably part of the equation for kickstarting self-reproducing structures, life, but we don't know for sure. And so it's possible that there are other places where life could be incubated. So even in our own solar system, we have evidence that 4 billion years ago, some of the larger asteroids, which can have a lot of volatile compounds like water and carbon dioxide and so on, may have actually been sort of moist or part of a larger body that was the wet and moist. And so most recently, there have been some fabulous results from asteroid samples brought back from an asteroid called Bennu. So there was a mission called OSIRIS-REx that sampled that asteroid and brought those samples back to the Earth. And what people are learning from those samples is that Bennu, the asteroid, which I've forgotten how large it is, but it's a sizable asteroid, has evidence of minerals and chemicals that were once part of essentially an aqueous environment, a watery environment, which is very strange, very interesting. And I don't think we know yet whether that's because that asteroid was part of a larger object that somehow broke apart or was fragmented, or whether in the early solar system conditions allowed for that, in which case maybe the same sort of chemistry could have existed on a much smaller body than a planet. And then we also look at icy moons in the solar system, places like Europa and Enceladus. And these places have interior oceans of liquid water, even today, and they're capped with ice. The ice may be tens of kilometers, hundreds of kilometers thick, so it's ice very, or it's water that's very much isolated from the space around it. But there's evidence of chemistry in those oceans. Most recently, there's been analysis of data from the moon Enceladus around Saturn that suggests there are organic compounds in that liquid water ocean beneath this icy cap. So so the question of, is a planet the best place for life? I don't think we know the answer to that.
Yeah, so many questions that we don't know the answers to. Another one of those types of questions is one from our listeners that is somewhat related. He goes by the online name JASourUNIL, and he asks, is there another separate domain of life with an independent origin that we have failed to recognize already on Earth? And I realize nobody has the answer, but maybe thoughts on.
But it's a good question. It is a good question, and people have considered the possibility of a so-called shadow biosphere. So the idea that maybe what we call life is just any phenomena that carries information, that is complex enough that it can reproduce, that it can undergo selective evolution. It can utilize energy. It can do all the things that we associate with carbon chemistry-based life. But maybe there are different ways to construct that. And so the idea of a shadow biosphere is that maybe there is an alternate biochemistry. It may still be carbon-based, but it could be sufficiently different that none of our present techniques for detecting the presence of life would have it show up. I think people perhaps don't always realize that most of life on Earth is microbial, right? In terms of mass, in terms of genetic diversity, and so on. Most of life on Earth is single-celled bacteria or archaea, which is the other type of single-celled microbial organism. And we've barely scratched the surface in terms of decoding the different species, understanding exactly how each of them operate. We think they all work basically with the biochemistry that we're familiar with. But the tools that we have to detect those organisms can often fail. There are many species of bacteria that don't show up in your petri dish when you try to, scrape them onto the agar gel in your petri dish, and they're not going to grow because they don't like it there. And so in past years, you might have concluded there's nothing there. We now know with genomic tools that there is stuff there. So the idea of a shadow biosphere is really intriguing because it's not inconceivable, especially at the microscopic level, that there's are forms of life that operate so independently of everything else that, they don't interfere with each other. We don't interfere with them, they don't interfere with us, and we might not notice that they're there. They might not be there in great number, because then I think we probably would notice, but it's possible they're there in smaller numbers. So it's a great question. It's something I think in astrobiology we have in the back of our minds to be, the term we use is agnostic about trying to find life, because maybe on Mars there's life that is just very different. And, it's a challenge to find it because of that. But it would also be really interesting and extraordinary. And just to add the one other thing, if we found a shadow biosphere here on the Earth, what would be really beautiful about that is it would tell us that it would immediately change the statistics about the likelihood of life elsewhere in the universe. Because if life can happen not just once, but twice on the Earth, that tells you that the odds of life happening elsewhere go up dramatically.
And to your N of 1 question, then we'd have an N of 2 in a
Yeah,
way. I mean, not a second planet, but a second biosphere within the planet,
absolutely.
and maybe a lot
Absolutely.
more
Right
to
here
look
under
at.
our noses, which would be amazing.
Yeah. Yeah. So back to our idea of information, will our collection of information be limited in some way over time? Are we approaching a cap of how much information we can gather for all of this research?
When you say information, you mean in terms of the sort of total human information,
Yeah.
or in terms of, yeah, so there is a connection between that actually and space exploration and the possibility of a future where life from Earth spreads further afield. So, we have a long way to go before we convert everything on the surface of the Earth into data centers, if that's part of what you're you're talking about. Our seeming ability to generate new information and store it currently is not particularly bounded. It is bounded by energy and time. It takes time to convert silicon into silicon chips and memory devices, and it takes time to build energy power sources and so on. There's an interesting question about just, how far can that go? I mean, it may be that at some point we realize that the detrimental effects of turning that much matter into information storing devices and generating that much power to drive them, the detrimental effects of that on the Earth's environment suggests that actually to keep going, we need to move off world. And so people have actually already been talking about, what about data centers in orbit? In space, you have much greater access to solar power. You're not sort of pumping clean water all the time out of a river and polluting it. In principle, you can build your data centers in space and perhaps make them much more efficient. And, you can keep going from there. In that sense, there's very little cap. I think the biggest constraint to the growth of information right now may actually be the utility of it. And the utility comes from our capacity to search it and to locate what we want. And you see this with the big large language models. They need to ingest a huge amount of data in the form of written material. And people are already discussing, well, are we sort of running out of original written material? And so what do we train these models on to make them better? Or do we just generate random stuff? Well, that doesn't sound like a good idea to me. That sounds like a route to disaster because it's just sort of self-reinforcing nonsense. I don't know the answer to that. What is the true limit to human information? That will come down to our creativity. The one thing we can do as biological entities is be truly creative. And I think that still holds even in the face of AI. True open-ended creativity, true generation of novelty is still a biological domain. That's still us. So it may be constrained by, how many good ideas we can come.
When you say true creativity is still us, what do you mean by that creativity?
I mean, the ability to generate, so in computer science, this is called the problem of open-endedness. Okay. And that refers to a mixture of generating truly novel concepts, but that are still grounded in truth and in reality, right? So I can say, yeah, pink elephants, right? But okay, pink elephants don't exist. Maybe they never will. But I can say, oh, actually, there's a subspecies of elephant that exists, and that's, a new thing. Or I can conjecture something about, the future of elephants or other things. So the capacity to also solve problems in innovative and interesting ways. Yes, some AI can sort of do some of that, but it's still very much something that we rely on humans to do, or other life. I mean, life is constantly finding innovative solutions to real problems. So that open-endedness is something that has long been sought in computer science, but never really achieved. So it's the ability to piece together seemingly disparate pieces of information and generate something new that is meaningful. Not sure we're quite there yet with large language models or anything like that. So that's what I mean by the sort of open-endedness, endless innovation, endless novelty. There's something about our biological minds appears to allow us to do this and just to keep going and to keep building on previous ideas, but adding new stuff constantly.
Well, for people who want to follow along with the new stuff that you're doing, where should people look for you online?
So I have a website, www.calebscharf.com, but I'm also kicking around on Twitter, on Blue Sky, on LinkedIn. If you search for my name, you'll find me.
Great. We'll put some links in the description and links to your books for people to check out.
Yes.
And Caleb Scharf, my last question is, what do you hope comes from all of this work that you do in astrobiology?
Well, I hope it improves our species a little bit. I would hope that it creates the conditions where we might discover something new and wonderful about the universe.
Well, it's a beautiful note to end on. Caleb Scharf, thank you so much for your work, for your books, and for taking this interview with me. I really appreciate it.
My pleasure. Really great to talk.